Well, hello, everybody. I feel like through all the videos that I've made for this module, that there's something I need to reconcile, and that's classical probability and empirical probability. And I'll do that in terms of a scenario that we could actually try out if we wanted to. Okay, and I'll show you how that would work. So I want you to imagine that we roll a die, and then I ask you what's the probability of rolling a 5. So we've seen questions like that already throughout the module. And one way that you could go about answering it is you could say, well, the probability of rolling 5 is 1 out of 6. Because there's one way to roll a 5 out of 6 possibilities, right? I mean, I rolled this die. There's only one way a 5 is going to come up, all right? And that's if the number that you see on the die facing up is a 5. But there's 6 total outcomes. Any of these numbers could show up, and there are 6 numbers on this die. So that's called classical probability, where it's like I don't actually roll the die to figure that out. I just know there's one way of the event happening out of 6 possibilities. But I'm curious because we actually could take a die like this and we could roll it and we could see what happens. Okay. So before I made the video, I did a little experiment taking the die and rolling it. I said 10 times. Okay. So I rolled the die 10 times and I compiled the results on this table. So when I rolled the die 10 times, I rolled a 1 4 times, a 2 2 times, a 3 1 time. I didn't get any 4s. I rolled a 5 3 times, and I didn't get any 6s. And if you count that up, 4 5 6 7 8 9, that's 10 rolls. Okay. So according to this, well, this seems very at odds with my classical probability answer. Okay. So here I said, well, it probably would be 1 out of 6. But when I did this actual experiment, actually rolling a die, it looks like 3 out of 10. All right. I rolled a 5 3 times out of 10 total rolls. So those aren't the same number. 1 out of 6 is not the same as 3 out of 10. What's the deal? So there's a few things that could be going on. It might be that this die is weighted in a way like it's made to cheat or something like that. You know, maybe this die is weighted so that like a 1 comes up more often or a 5 comes up more often. That could be true with this die. I don't know. I don't think it's an unfair die. I mean, looking at it and feeling it, I would think any number is equally likely to come up. But that's one explanation. It might be that this die is just not fair. It might be that it favors certain numbers or a certain number over the others. The other answer that I think is the truth about this die is that, well, if I were to roll the die more times, these probabilities would all even out. Okay? Meaning the frequencies would even out. Like I would get a 4 just as much as a 2, just as much as I would get a 1 just as much as a 2, as much as a 3. Like it wouldn't be that I rolled one number way more than the others. That's called the law of large numbers. And I think that's actually how we could reconcile these numbers. I think that if I took this die and kept rolling it, and I don't know how many times I would have to do that, but if I kept rolling it, who knows, maybe 100 times, maybe 1,000 times or more, I don't know, then these frequencies would even out and each roll would seem to be equally likely with a probability of 1 out of 6 once you reduce the fraction. Now, I don't really want to roll this die that many times for the sake of the video because I might have to roll it, like I said, a lot of times. So I'm trying to see if there's another way that I could test this out. Okay, so I'm going to put this die aside because I don't think for the video it's too practical to roll that 100 times. But if I go to my math lab and I open StatCrunch, there's a way that I could try this out. All right, I could go to applets and simulation, and here it allows me to simulate various uncertain things like flipping a coin where you never know if it's going to be heads or tail, rolling a die, you never know what number is going to come up, so on. So it allows me to simulate that. I'll select a 6-sided die and I'm just going to roll it one die instead of 2 dice. Okay, and I do a compute and then I can figure out how many times I roll the die. So let's do like one run. Okay. Whoops. Okay. So if I rolled a 1 time, it came up a 6, just as a simulation. It's popping out a random number according to what a fair dice would be. What if I did 5 runs? Okay. All right. So it looks like if I roll 5 times, then I rolled 3 twos, 2 threes, and then 1 6. That's the 6 I already rolled before. Okay. So this is 6 total rolls. Now, what was my claim? So I don't get off track. I can reconcile the difference between classical and empirical probability by rolling this die a bunch of times. Now, I don't know how many times a bunch is, but let's just keep going and see if it evens out. I'm going to go straight to 1,000. What if I rolled the die 1,000 times? Do you see how now they're roughly evening out? I rolled more ones than any other number, and I rolled fewer sixes than any other number, but they're close, right? Here it says I rolled 173 ones and 169 twos. They're pretty close. They're not totally equal, but that's a lot closer to them being all 1 out of 6, it turns out. I could keep going and I could do 1,000 more times and 1,000 more. And if we just keep going, we'll see that, yeah, individually they may bump up or down, but they're going to even out more and more if I keep going. Now they're looking pretty level. And I imagine if I keep going, here I'm up to, if you can imagine it, almost 9,000 rolls of the die. Then they're hardly different than each other. Okay? And then here it's like hard for me to tell they're different at all. They all look about the same. Okay? It looks like any one of these numbers came up just as many times as any of the others. Now, in that case, if I rolled the die 9,952 times, what's the probability of rolling a 5 then? Okay, in contrast with my experiment over here of actually rolling the physical die 10 times. Well, let's calculate. I'll pause the video to calculate it and resume it once I get you the number. Okay, so I wanted to calculate the probability of rolling a 5 based on this extremely large number of individual rolls of the die. And looking at it, I got 3,531 fives out of 21,006 total rolls. Okay, so let's calculate this way. Whoops. Okay, pardon the technical problem. I had to update this thing. So I had to add another 1,000 rolls in it. So that is 3,531 fives out of 21,006 total rolls. So, okay, the probability there, probability rolling a 5 based on that experiment is 3,531 over 21,006. And if I get my calculator, that rounds out to be about 0.168. That's based on those, not 20,006, but 21,006 rolls. Now, okay, does that reconcile the difference between empirical and classical probability? Because remember, I told you when I started this, I said, well, if I just think about what the odds of rolling a 5 should be, it's 1 out of 6. But then if I roll the dice, it seemed like 3 out of 10 until I rolled the dice a bunch of times. And my prediction would be that these numbers even out and that the probability of a 5 or any other number is 1 out of 6. So in order to compare these, in order to see that, you know, this does lend to the prediction that the odds of rolling a 5 are 1 out of 6, in reconciling classical and empirical probability, I got the decimal, right? So 1 out of 6, if you divide it, is 0.167. And here we just did this one from rolling the die more than 20,000 times. And it turned out the probability of rolling a 5 was 0.168. Those are very close, okay? And they would only get closer and more alike if I were to roll the die more times, okay? So I hope you forgive me because I wasn't going to roll this die 1,000 times or even 500 times, but I really did want to show you that, yes, as we roll more and more and more, empirical probability may vindicate classical probability. Okay, what's the exception of that? If this die wasn't fair to begin with. Okay, if it was weighted, if it wasn't really the case that any one side was just as likely as any other side to roll up. All right, so that combines a number of different things from this module. It goes a little bit beyond what our assignments are, but nonetheless, I hope it helps you understand things a little better and think about them in a more interesting way.